Okay, so in this video I'll be talking about rotations in quantum mechanics. So the topic is rotation in quantum mechanics. Now let me first discuss about the two viewpoints of rotation. One is active viewpoint. So let me start with a coordinate system. Let me start with a coordinate system. This is x-axis, this is y-axis, and there is a vector v. After rotation it ends up at v prime. So this is v, this is v prime, v vector, v prime vector, and it rotates in an angle theta, and suppose this angle is alpha. Okay, so this is the active point of view in which the vector itself rotates and the coordinate axis is fixed. And there is also a widely accepted viewpoint is passive viewpoint, PP. So the passive viewpoint is the vector is now fixed in space, but the coordinate axis that is rotated. So the coordinate axis is rotated like this with an angle theta. This is theta, this is theta. So in before rotation, so this is x and y, and after rotation it goes y prime and x prime and x prime. So let me see how this v and v prime are related. First of all, the magnitude doesn't change. Magnitude of v is magnitude of v prime, and let me call it v. Okay, now let me work out the components. Let me work in active viewpoint. So in active viewpoint, the vector rotates and the coordinate system is fixed. So in this case, we are interested how the coordinates are related to each other before and after rotation. That is how the components are related to each other before and after rotation, not coordinates. So in this case, I just take like this. Now if we draw the components, this is the components before rotation, Vx, and this is Vy. Similarly, after rotation it gets Vx prime and it is Vy prime. Okay, so now Vx is written as V, this is cos alpha. Similarly, Vy is V sin alpha. Now from the picture, Vx prime is, this is V prime cos theta plus alpha, and Vy prime is V prime sin theta plus alpha. Okay, now we can write V Vx is v prime is actually v from this criteria that the magnitude of the vector doesn't change. So it is actually Vx is v cos theta cos alpha plus minus sin theta sin alpha, and Vy prime is v sin theta cos alpha plus cos theta sin alpha. So ultimately we obtain Vx is v cos alpha is just Vx, so Vx prime is v cos theta Vx cos theta minus Vy sin theta, and let me write it curly v because I'm accustomed with writing v with this curly thing. So this is Vx sin theta plus Vy cos theta. Now let me consider infinitesimal amount of rotation. In that case, let me denote the rotation angle by delta theta. So we rotate the vector with angle delta theta. So since we are working in infinitesimal domain, we have cos delta theta, we can take it as 1, sin delta theta is delta theta itself. We neglect here, the working principle is neglect delta theta's order of delta theta square and higher terms. So in that case we have Vx prime Vy prime, Vx prime is Vx minus delta theta Vy, Vy prime Vy plus delta theta Vx. Let us define delta Vx as Vx prime minus Vx, delta Vy as Vy prime minus Vy. So this is actually delta theta Vy, this is actually delta theta Vx. Okay, now note that v is any vector. It could be a position vector, it could be a momentum vector, or any physical vector. So let us consider Vx as position vector. Then this active rotation, after active rotation, this position, this coordinate x and y, this coordinate goes to x prime y prime, which is equal to x minus delta theta y and y plus delta theta x. So this is active rotation. So now after this, so now we are interested how this active rotation takes a quantum state gate. Okay, so let us call this rotation, before proceeding let us call this rotation as a matrix Rz delta theta. In this case it is written as minus delta theta 1 and delta theta 1. Am I right? Yeah, I'm okay. So now if we write in a matrix form, then x prime y prime is related to x and y with this rotation. X and y. Now in quantum mechanics, for every rotation or every unitary transformation has every unitary transformation is implemented by a unitary operator that acts on a state that acts on the states belonging to the Hilbert space. That is, for Rz delta theta there is an operator mapping kind of thing, Rz delta theta, which for convenience I write it as u delta theta. Okay, so this thing acts on points, this thing acts on state gate of Hilbert space. Now we have what we are after. We are after this quantity. What does this u Rz delta theta does to a quantum state gate psi? So we are after a state gate after transformation is written as u of delta theta. This is an operator, u of delta theta psi. So this is the final result of a rotation of a state gate. After rotation, active rotation, psi becomes psi prime. This is the thing. Now think of a particle, quantum particle, which is in a definite position eigenstate. So it is precisely located in this region, although we cannot determine the position of a particle in real life with 100% accuracy, but for our theoretical work let us assume that. Now for the active rotation, you just rotate this particle by an angle theta. So it just travels down by an angle delta theta to x prime y prime. Or we can think of it as we have that particle at x and y, and I come silently and rotate this coordinate axis. Okay, sorry, it should be in this direction to have the equivalence. Rotate that coordinate axis along this delta theta. So after this rotation, we have this position of new position should be related to the old position like this, where we have x prime is just the same as x minus delta theta y plus delta theta x. So this is our starting point. Exactly, we are interested in computing this quantity xy u delta theta psi. This is x comma y psi prime. This is psi prime x comma y. Now we write it as psi prime, and in between we insert a complete set of states. Here we insert complete set of state, the resolution of identity like this: xy xy psi. Okay, so we have inserted the resolution of identity, the resolution of identity dx d capital Y. Note the capital and small. Here I use xy equal to identity operator. Now we have psi xy is equal to d capital X d capital Y x comma y. This becomes x minus delta theta y. We use the property of u theta, that is when u theta acts on position eigengates. Y plus delta theta capital X. This is psi capital X capital Y. Okay, now we want to make a change of variable. Let us call this zeta equal to delta theta y and xi equal to y plus delta theta x. Now dx dy is written as determinant of a matrix called Jacobian and is mod absolute value this should be d zeta d xi is determinant of this Jacobian. This is J is Jacobian with dx d capital X d capital Y. Here J is defined as delta xi delta X delta xi delta Y de zeta delta Y delta xi delta X delta xi delta Y. Okay, so I could sometimes just while talking I call this zeta xi, so sorry for that mistakenly. Anyway, so this is 1 minus delta theta 1, this matrix. So date of J is actually nothing but delta theta square. But as I mentioned earlier, we neglect delta theta square as it is second power in delta theta. So in this approximation we have d zeta d xi is dx dy. Now if we invert this equation, then we get x is zeta plus delta theta xi and y is delta theta minus delta theta zeta plus xi. Okay, so let's put it there. Psi of this psi prime of x and y is d zeta d xi, and there we have x y, there we have xi zeta xi, and this is psi of x and y were earlier capital X and capital Y, so it is replaced as delta theta zeta minus delta theta xi. So this is the thing. Now we know this is equal to t psi. This is equal to nothing but x minus zeta delta y minus xi from the orthonormality condition of this position ket, psi zeta plus delta theta xi minus delta theta zeta plus xi. This. So ultimately what do we have? We have this relation psi prime xy is equal to psi of x plus delta theta y after doing this integration minus delta theta x plus this y. Now we Taylor expand this psi, this thing, Taylor expand around xy. So this becomes delta theta y. This is, you can think about this delta x, delta psi delta x minus plus this minus delta theta x. This is, you can think as delta y, delta psi delta y. Therefore let me write it. Therefore this psi x comma y plus delta theta y delta x minus x delta y of psi xy. Now we know the angular momentum operator is r cross p. This is the operator. So Lz equal to x delta y x p y vector y px vector. So Lz is, we replace this py vector in its position space representation, and thus we get IH cut delta y minus y delta x. So this equals y delta x minus x delta y, which is our requirement. This is equal to minus I by h cut Lz cap. Am I correct? Yeah, that's correct. So we have psi prime x comma y is psi x comma y plus, sorry, this is minus delta theta I by h cross Lz psi x comma y. Therefore we can write it as delta theta I by h cross Lz psi x comma y psi prime x comma y is equal to this. Note that here Lz is the position space representation of the angular momentum operator L vector and its z component. So now what is the conclusion? The conclusion is for a rotation around with respect to z-axis or around z-axis, the generator is Lz. The z component of angular momentum, or we can say that the z component of angular momentum generates a rotation of state gate around z axis. Therefore, now note the generator term. So this is a generator. It is actually called generator in the terminology of Lie group. So we can say that the angular momentum terms are generators of rotation. So in other words, the x component of angular momentum Lx generates a rotation along x-axis. Similarly, y component generates a rotation along y-axis, z component generates a rotation along z-axis.